So now that we have our neighbors returning, the next thing we want to do is return states as well. So we can add a comma down here where we're calling that get image neighbors and add states. And these states are going to be a 1 or 0 value, so a black or white, a binary output, essentially a Boolean value, telling us whether our current pixel and our neighboring pixels, whether they are white or black. So in order to do this, we can first test our current point, which is image point. So if self.image of image point, and before we maybe do this conditional, we can just print this and see what that actually gives us. So it's actually throwing an error because it's reading that index as something other than in ellipses. So if we just add this line here, image point equals, and then separate out these indices, so 1 and then 0, image arrays have a different prioritization than our coordinates from the Rhino client. Basically, instead of rows and columns, it is columns and then rows. So if we just flip that and then set that equal to our image point, which is really our image point index, and then print self.image with that index value, then we get 0. So this is a black current pixel value. So what we want to do is say, if that value is less than 127, which is about the midpoint between 0 and 255. So if that is less than 127, then states equals, and we're going to make a list and place that first item in that list of 0. So if it is less than 127, it is black, which we give it a state 0. Else, meaning it is white, then we're going to set states equal and then feed in the first item in that list, which is going to be 1. The next step is going to be to cycle through each of our neighbors and append each one of our neighbor states to the list of states. So we can say for neighbor in neighbors, and then this same statement here. So if our image color value at the index, in this case it's going to be neighbor, is less than 127, then states now .append, because we don't want to override that first item, so states.append, and we are going to input 0, else states.append 1. Then we want one more thing before we leave this function, is we don't want just our neighbors and our states, but we actually want our image point index as well. So we're going to output image point, neighbors, and states. Since we're returning each one of those, we need 3 values separated by commas set equal to that, and it will parse each one of those values. So image point will be fed into this variable image point, neighbors into image neighbors, states into states. We can now define our vec based on those criteria. Okay, in order to define our vector, first we should create a variable vec and set this equal to create vector 0, 0, 0, so a 0 length vector. And now we're going to just add to this vector, and we want to do this by cycling through. We want to do this by cycling through each of our neighbors, checking their states, and if their state is black or 0, then we want to put them in a kind of option pool that we could move to. This is going to allow us to trace the black edges of our adaptive threshold. So if the state is 0, then we want to find the pixel that is closest to our current heading. So this means if there's only one behind us to the right, then we can change behind us to the right. So then our heading changes to behind us to the right. But if there's one behind us to the right and there's also one ahead of us directly in front, we're going to just keep going straight. So this is a relatively narrow neighborhood understanding. One way of improving on this basic introduction method is to expand the neighborhood, but we don't want to use computationally costly search algorithms in this case. So this is going to be for hopefully relatively efficient computation of a kind of basic agent navigating an image. So the first thing to do is to say for neighbor in image underscore neighbors. And we actually don't just want our neighbor, but we also want an index value so that we can call items from the list of states as well. So for I neighbor in enumerate image neighbors. And then inside of that loop, we can say if states, and we would say here if states of I, but because we actually included our current point there, we don't want our current point to be calculated. So we want to skip the first item, which means we want to always add 1 to our index. So I plus 1. That way we don't start at 0, we start at 1. And this will coordinate with our neighbors list. So if states of I plus 1 equals 0, so testing the equality there, if it equals 0, then we're going to compare the angle between the vector from our current position to that point with the current vector heading. So our self.vec property. So first we want to make a target point. So this is going to be the point relating to this state or that neighbor. And this is going to use a method that is incredibly long, but it will throw errors if you don't write it exactly like this. So we'll go through each step of it. So I'm going to just expand this so we can actually look at the whole thing. If we break this down a bit, I'm going to comment that line out. All this is target equals rs.create point. And then inside of these parentheses, we're going to add our point definition, so our 3 coordinate values. Now, what we want is to convert our neighbor index values, so our pixel space or image space values, into an actual coordinate point in Rhino space. So we can do this using se.doc.views.activeView, or if we wanted to, we could just use the my image, and then that is a property in the class reference image. So we have there self.view, so my image.view, and then use the method screen to client point, screen to client. This method is going to do that matrix transformation from our screen space and project it into our Rhino space. So what we would want to do is input our neighbor and then close parentheses. But if we print this, so if we just hit test to print this, capital I in my image, it says here expected point 2D instead got tuple. So let's just go ahead and print neighbor and take a look at what that is outputting. So it's taking this as an actual index value of 2 values, but it's registering it as a tuple, not a point 2D. So if we try to coerce this and say rs.coerce 2D point, so this coerce 2D point actually seems to be working. So we can just use this for now. And we're going to go up here and say our target now equals rs.create point, and we can print target. It looks like we still may need to, even using this method, we still need to specify a first item, paste, specify that next item, and then a 0 to convert it into 3 coordinate space. And now if we hit test, that should work. Yeah, so it looks like that is working. So it's pretty similar to our original one. Technically, our screen to client method takes a system.drawing.point, which is a system method. So it's a bit different, but effectively, we still have to take our coerce 2D point and extract each item separately. So we have my image.view.screen to client, rs.coerce 2D point neighbor, which is converting a tuple to a 2D point. And then that first item, so the X value, and then the Y value, and then our Z is just going to be 0 because it's flat, and we know that our view is. Okay, so now we have our target point. So if we want to find our target vec, we can subtract our current position from our new target point. So target minus self.pos and print target vec. This will give us our target vector value. Okay, that seems to be working. And now what we want to do is say angle equals rs.vector angle, and we're going to test how close this target vec, so paste this in, how close that target vec is to our current vector heading. Then we need to say if angle is less than our smallest angle, so our closest vector to our current heading. So this is going to require a new variable called closest angle. So if the angle is less than the closest angle, then do something. But first we need to actually specify this variable up at the top. So closest angle equals, set our closest angle equal to a high number so that all of our angles are going to be lower than this, so it'll override. So if angle is less than closest angle, first thing we need to do is set closest angle equal to angle. So our new closest angle equals the angle that was lower. And then we need to set vec equal to our target vec. Then as an error trap, just in case for some reason we can't find neighbors or some other thing goes wrong, we need to say if rs.vector length of vec is 0, then vec equals self.vec. So basically, we just want to keep going the same direction if our vector is 0. That way it avoids, for some reason, not finding neighbors and then just staying still forever. So now we can uncomment this down here. So self.vec is going to be equal to our vec, and then self.pos plus equals self.vec. Now if we hit test, so right now we're getting an error because we're now moving these agents far in the coordinate space so that they're actually outside of the screen. And then that index value, because it's outside of our screen space, when we convert it to screen space, it's giving us this outrageous negative 19,967. So first, let's just see if it works if we do one step. Okay, so it works if we do one step. But what we're going to want to do is have a check that says if this agent is getting too close to the edge of our screen, then we want it to actually turn around. So we want that vector to reverse, and we want the agent to turn the other direction and then start heading backwards. So to do that inside of our agent, we want a vec bounds. We want to feed in self. And then what we need is to know our current index. So our current index value, and we want to say if this index is getting close to the bounds of the screen. So if the index is below 0 or getting close to 0, or if it is approaching the size or of the width or height of our image, then reverse the vector. So the first thing we need is actually another property in our agent class called self.index, and we can set self.index equal to our image point index there. And now we can use that image point index inside of our check bounds function. Then we want to create a conditional. So if self.index of 0, and we'll say is less than 0, or we're going to have a string here of conditions, which are going to basically give us the bounds of each side. So each of the 4 extents of our axes. So if self.index of if the first item of self.index is less than 0, or if the first item of index is greater than, and now in this case we want my image.image, and we want the shape of this image, so shape 0. And then we want to do the same thing with our other item. So you can actually just copy these now. Say, or the second index item is less than 0 or is greater than the second axis of that image shape. So essentially trying to keep it in those bounds. And then we want to say, if that is true, then self.vec equals equals rs.vector reverse, and then feed in self.vec. So if these conditions are true, which means we've passed the bounds, then we want to reverse our vector. Now, this seems like it may work because we're having a error trap here, preventing it from going beyond the bounds. But What this doesn't do is prevent it from hitting the bounds, which will still cause an error. And it may not prevent it if currently it's not breaking the rules, but in the next step it is going to, then it will still pass an error. So we actually want to create a margin for this bounds, and we can set this margin equal to, let's say, 20. And instead of 0 here, we want to add in our margins so that we have a margin from this border. So let's say we want our actual space of operation to be about there, then this space here is going to be our margin in both of these axes. So we can just use the margin value of 20, and we're going to say if it's less than our margin, or if it's greater than the shape, so that width minus our margin, and then here again, less than our margin, or the shape minus our margin. So now, if we get too close to our borders, we're going to flip that vector. So this should work. We should now be able to hit test. We've declared self.index, but set it equal to nothing. So we need to say self.index equals, and we can just say none first, because we're going to override that value. Okay, we don't get any errors, but we're not actually visualizing anything. So hopefully this is familiar, but we're actually going to add trail points. So this should look relatively familiar. Set this equal to a blank list. And then inside of our constructor function, we can just already append our first position. So append self.pause. And every time we run the move, we want to append our new self.pause to our trail points list. Then at the bottom here, we want our variable output t. So we want that output t to equal a blank list. And then we can say for agent in population, trail equals rs dot add interp curve, and then we're just going to feed in agent dot trail points. And then we want to make sure that we're appending to our list t all of our trails, so append trail to t. And now if we hit test, we see our trails being appended there, and they seem to be zooming off in space. Another option would be to limit our vector. So instead of just always resetting self.vec equal to vec, what we can do is actually say plus equals vec. So we're always adding to the previous vector with our new vector heading. And then we can actually just say self.vec equals rs.vector unitize self.vec. And this is going to make sure this is going to constrain the vector to a velocity of 1, or a vector length of 1. And if we wanted to control this a step further, what we could do is actually add a coefficient here, or a factor to limit this. So rs.vector scale, and this is going to scale that vector based on a specific weight. So if we already know what we want to limit this to, then we could just say 0.5. But a better way to do that is to create a property in our class, and we can call this property self.maxval, and we can set this here equal to 0.2, and then use that property to scale our vector before it gets added to our point position. Now if we hit test, we can see it's now moving in smaller increments, which is going to be a little bit more optimal. Now if we scroll down to the bottom and increase our step size, or our steps to 20, and hit test, we should be able to see larger trails drawn out in our image space. Perfect. And they seem to be at least making some responsive decisions relative to their immediate neighbors. So they're tracing some of these corners, which is good. Now we can try and actually set a few different lines. So instead of 3, let's right click on this, set multiple lines. And let's see if we can get these to respond to our image in our Rhino space. So hit enter to set those lines, and then we'll see them run with reference to our image. Okay, so it looks like it is doing it, but we can see that there's no coordination between these agents. They're all running completely separately. They're occasionally picking up pieces and starting to turn and adapt, but that adaptation is happening too slowly to continue to kind of move either along the image, or to pick up maybe their neighboring agent and start moving in coordination with them. So in order to program this coordinated movement, we want to add a few more functions inside of our agent class. One is going to allow our agent to seek the immediate neighboring agents. So we're going to use a search algorithm to find the nearest agents. And then if there are any near agents, then we're going to cycle through and seek the average position of those agents. And then we want to add one more piece of functionality, which is going to allow us to actually not just seek our neighboring agents, but to follow their trails if they've deposited trails in front of us. So first, we're going to look at a function for allowing each agent to know its neighboring agents and then to seek those agents. So we're going to want to do this just before we actually update these properties here. So we can just hit enter a few times to provide some room there. And we're going to say here, find neighboring agents. And then we're going to say below that, update seek vector. And then we're going to add that vector with a factor weighting or scaling to our existing vector here, reading our image data. Okay, so first find the neighboring agents. We need to create a function inside of here, and this is going to be called get agent neighbors. This is going to be a function inside of this class, so self.getAgentNeighbors. And now we need to make this function so we can make it below our check bounds. Get agent neighbors, feed in self. And now inside of here, we're going to use our search algorithm as our method for finding our closest agent neighbors. First, we need a list property called self.agentNeighbors. And we're going to set this equal to a blank list, so it updates every single time we call this function. And then we need to instantiate a tree, so Rhino, so our tree equals rhino.geometry.rTree. This will initialize an object of type rTree, and we're setting that equal to rTree. And then we want to loop through all of the agents in our population. So for I item in enumerate population, we want to insert each one of these into our rTree. So rTree.insert. And the first item we want to insert is actually our item's position, so our agent's position, so item. And we're using the property position, so item.pos, and then the index in the population list, so that's I4. Now we've inserted each of those. We now need a geometry reference to search, so search here equals rhino.geometry.sphere, which takes an input point and a radius. So in this case, our input point is self.pos, which is our current position because we're seeking all of the neighboring agents near our position. And then our radius is going to just be self.radius, which we now need to create a new property at the top, self.radius, and we can set this equal to some value. Next, we need to specify a callback. So we can type rTree underscore callback equals, and now we need to type lambda sender, comma, space args. Next, we want to specify what we want this search algorithm to do every time when it finds an item that satisfies this argument. So in this case, we want to say self.agent neighbors.append. So we're appending to this list of agent neighbors, and we're going to append args.id, which is this second value here, which is our index in our population list. And now we just need to call the actual search. So rTree.search, open parentheses, and this is going to take an input geometry, our search sphere, and our callback. And now we don't have to return anything because these self.agent neighbors will exist as a property for the entire class. So now we've found our neighbors. We now want to cycle through each one of those neighbors within our radius, and we want to create an average vector between all of them. So this is going to be another method called self. And for this method, we actually want to return a vector value. So we're going to return vec1 and set that equal to seek agent. And now we just need to make that method. So def agents, input self. Okay. So for this, we want to cycle through all of our neighboring agents, find their current positions, make a vector between our self.position and their positions, and then average each of those vectors up. So we're going to say vec equals rs.create vector 0, 0, 0. And now we need to say for agent in self.agent neighbors, for index in self.agent neighbors, vec plus equals, because we're going to just add directly to this vec. So vec plus equals not our self.agent neighbors and not our index, but we want just our index value from our population. So population index, and then the position property. Then we want to subtract that from our current position, so self.pos. Now that's just adding them all together. We now need to scale those based on the length of our agent neighbors list. So vec equals rs.vector scale, input vec, and scale it by 1 over length of self.agent neighbors. And now we can just return this vec. And we're almost done. We have this additional vector here. We just need to add this to our other method of constructing a vector, so our pixel-based or image-based one. So right now we have vec and vec1. So we can say total vec equals, and then we're going to add vec1 and 2, but we're actually going to do a weighted average between those. So we can say rs.vector add, and we would just say vec comma vec1. But since we're doing a weighting between those, we actually want to scale each one. So rs.vector scale, and this takes a scale factor, which is just going to be a float value, which we want to actually make a new property for. So the first one will be our self.image scale, and then the next one will be our vector scale self.seek scale. Now we need to add both of those properties at the top in our constructor function, and we need to set them equal to some float value as a percentage to scale those vectors. So for now, we'll set image scale equal to 0.8 and our seek scale equal to 1.2. And now instead of vec, we can use our total vec, and we can still scale it by our maxvel and unitize that and then add it to our position. So now if we hit test, we should see those agents responding to their neighbors. Okay, so we can see that they are definitely seeking each other, and they're also trying to stay relatively close to the image values as well, but they're just seeking, but there still isn't much coordination. And you can actually see here that we have intersections between those trails. So one way to avoid this is to add a trail alignment function to this. So just under our get agent neighbors and then our seek agents, we can add def trail align feed in self, and we're going to create another vector here, which we can add to our total vec. And this vector is going to find the closest point on the neighboring on the curves, test its distance to our current point, and if it's inside of the, and if it's less than our radius value, then we will consider it and we will find the tangent to add to the alignment. So the first thing to do is call this below our seek agents, trail alignment vec2 equals self dot trail align. So now instead of just rendering our curves here at the end, we actually want to cycle through our population and our trail align. So we want to say trails equals rs.add interp curve, agent.trail_points is fine. So trail equals that, and then we need to say above that for agent and population. So we're just going to do it for all of them. For agent and population, add a curve, and then we want to find the closest point on that curve. So rs.curve closest point, open parentheses, and it takes an input curve and then a test point. So our input curve is our trail, our test point is self.pause, and this will give us an output number, which is the parameter of the closest point. So this is giving us a parameter. In order to convert that to a point, we actually need to say rs.evaluate curve, which takes an input curve ID, which is trail, and then our parameter, which is param, and it will give us an output 3D point. So now we have our closest point, and now we want to say distance equals, so dist equals rs.distance, open parentheses, and then it takes 2 points. So we need our self.pause and our closest point on that curve. Now, if distance is less than self.radius, which we've already defined for our search algorithm there. So if distance is less than self.radius, then we want to find the tangent at that point on the curve and average it between all other trail tangents. So we want to say tanvec equals rs.curve tangent. This takes an input curve, so trail, and then our parameter. This will give us a tangent vector at that parameter. And now we just want to go ahead and add this to a 0 vector. So create vector 0, 0, 0. And then we want to add tanvec to that vector. So vec plus equals tanvec. This will add it to our vector, and then we want to say return, and then we want to scale that vector by the length of our neighboring tangent vectors. So in this case, we actually need a count. So count equals 0, and then every time we do satisfy this conditional, we want to add 1 to count, and we want to scale that by 1 over count. So this will average that vector between all of our closest tangents within the self.radius value. So now our trail line will be outputting that vector, vector 2. We can clean up this notation now that we have more here. So instead of vector add, we can just directly add with math. So we'll just say, and instead of vector scale, we'll just say vec divided by vec times self.image scale plus vec1 times self.seek scale plus vec2 times, and we'll do self.t-align scale. So our trail alignment scale. And just to be clear, we can put parentheses around each one of those. And then we just need to make a new property, t-align scale, and we can put that under our other two. And we can just set this equal to 1.0 for now. And now if we hit test, we should see some more alignment between each of these agents. So we're getting an error here that we have insufficient points for an interpolated curve. This is because we don't have a conditional here. So it's trying to do this even from step 1. So we actually just want to put a trap here that just says only do this if if agent.trail points, so our trail points there, is greater than 2. So we don't need to do it if it's not greater than 2. And we can actually tab all of this in because this count is going to give us an error if it's still 0. So then we'll just say if not agent, but if self.trailpoints is greater than 2, because they all should have the same amount of trail points. So if self.trailpoints is greater than 2, then go through that, else return, and in this case, we're going to just return vec, which should be our 0 length vector. Now we can hit test. Okay, so now they're starting to align a bit more. And if we just go down to the bottom here where the steps are, we can increase this value, hit test again. So now we have them running a bit longer, but we can see that this actually causes a problem because our behaviors aren't weighted properly. So we can actually just go back through here and start adjusting these parameters. So maybe we actually want our radius to be 15 instead of 20, so the agents don't see each other until slightly later. And then we can increase our image scale, let's say to 1.2, and then maybe our seek scale only to 0.8. and our alignment to 0.4. And now let's try that and run it. Okay, so you can see it's starting to align a little bit more to those edges there. And if we just turn our seek down to 0.1, and then maybe just keep our alignment up and then hit test. So now we can see that our agents are not converging at all, but instead are aligning slightly and are trying to align with some of these edges in the image. So they're starting to kind of read the bundling of these edges there. But I think more exciting is moments like you can see there where the agents are independently reading those neighboring pixel values and adapting their course. You can see it happening slightly here. You can also see it happening really successfully on this guy in the scene. So the agent is actually coming up and tracing the crevice of the arm, and then it goes beyond. So no longer can it find neighboring pixel values. So no longer can it find neighboring pixel values that satisfy it. So it then carries on and picks up this next edge, and eventually finds the rest of the agent. So that is going to be all for this tutorial. But again, I think this workflow is a powerful one if you really think through the kind of potentials of it. So how might you be able to coordinate a view input or an image reference input to an actual 3D geometry being generated in a real 3D coordinate space? This can be done with multiple views or many other adapted versions of this method. In the next video, we're going to cover a similar topic, but we're actually going to add TensorFlow and look at reinforcement learning driving a very similar setup to this. The only difference being here we've explicitly described the behavioral weighting to the system. In the next video, we're going to look at how TensorFlow can actually define that weighting using reward functions inside of reinforcement learning.